In our previous video, Introduction to Case-Based Reasoning, CBR, we introduced a unique AI tool that relies exclusively on past experience to solve new problems. CBR essentially calculates the similarity between a vector of the main parameters of a current scenario and equivalent vectors of similar historic cases. In our example, we based the analysis on the Hamming local global classifier with its two-step process. The formulas governing the analysis are shown to the right of the screen. The primary dilemma in the example presented was, to what extent should rescue helicopter pilots, entering a combat zone, risk their own safety and that of their crews? Should they continue their final approach into harm's way, or is the risk too high, and a better choice for them is to abort the mission? The purpose of this effort was to create an outline for a CBR-based flight computer that would be at the heart of a future autonomous unmanned rescue vehicle. We showed a total of 14 parameters that form the main basis for the decision whether to continue or abort. These are the titles of the table shown as a reminder at the top. They include weather conditions such as winds and visibility, physical conditions at the objective such as obstacles, the extent of ground fire towards the helicopter, as well as its remaining fuel level and mechanical condition. Last but not least was the reported condition of the patient on the ground. The more critical that patient's situation was, the more risk the pilots were willing to take, up to a point where the risk is too high for the rescue helicopter, no matter how critical the patient is. In short, a very difficult situation for which there's no simple answer, and certainly no existing AI or other algorithm to trust. CBR is the only method that has a chance to be of help in the situation. To demonstrate how CBR works, we relied on 8 past cases as shown in the main table at the top. Below the table is a presumed situation that our future UAV could encounter, having to make a decision whether to continue or abort its mission. The way CBR works was described in detail in the previous video and we will not repeat it here. However, one part that we would like to concentrate on in this video is the list of weights, or relative importance, shown here below the UAV's vector, weights that are associated with the 14 parameters. These weights affect the significance attributed to each of the parameters by the pilots, and in the future, the UAV's computer. It should be noted that when we extract historic cases to support a CBR prediction or recommendation, the historic data usually has a description of most if not all of the parameters, but does not normally include any discussion on the relative importance of each one. Therefore, these must be externally added to the data. CBR will work also without attaching a relative weight to each of the parameters. But we know from experience that some are definitely more important than others, so there is a strong incentive to add those ourselves. But how will we know what values we assign to them? We asked the experts. And in the case described in the previous video, the experts were rescue helicopter pilots. Last time we also mentioned that there are 2 potential methods to construct the weights. The first was by interviewing the experts, which is what we did last time. Or, reconstructing the weights from the historic cases themselves, using machine learning with gradient descent. The machine learning method starts with random weights. We then iteratively test each historical case by making predictions about the decision, based on the current weights. We then update the weights with each iteration until we converge on the optimal combination that best reproduces pilot decision patterns, as reflected in the historical data. The purpose of this video is to explain how this second method works. Before we begin, it is important to note that as we saw in the previous video, CBR itself can function very well based on a relatively small number, even a handful of previous cases. However here, in order to extract the parameter weights from the cases themselves, we will need at least 75 to 100 historic cases. Here is how we expanded the historic cases database, adding 88 missions to the original 8, so now totaling 96 missions. And the weights are yet to be discovered. So let's see how this works. Here is our main flowchart. illustrating a systematic approach to extracting these hidden decision patterns, using a machine learning technique called logistic regression. We begin with the data collection phase by gathering historical cases where pilots faced similar decisions. As mentioned, each case includes the values of all relevant parameters and the actual decision made, continue or abort. In this example, and for simplicity, we did not consider other potential decisions such as go around and try another approach, land nearby, or other ideas. We just went with the two main ones. This defines the problem as a binary decision case, which is easier to illustrate. Keep in mind, however, that what we will show here can be easily expanded to a multivariable decision problem. As we recall, the parameters associated with this mission come in many formats. Weather might be described as good, marginal, or poor, while fuel level might be recorded as percentage of a full tank. We need to convert all these different types of information into common numbers the computer can work with. Good weather might become 1.0, marginal becomes 0.7, and poor becomes 0.2. This standardization ensures all factors can be fairly compared. This is the second block in our flow chart, pre-processing. The initialization phase starts with random guesses about how important each factor might be. These initial weights are essentially random numbers, which is a very common way in computer science and AI to start a learning process. The heart of our approach lies in the red-boxed iterative loop, where the computer gradually improves its results, through repeated cycles of prediction, evaluation, and adjustment. In the first, forward pass stage, the algorithm makes predictions using its current understanding of each factor's weight in the final decision. The algorithm examines each historical case and predicts what decision should have been made. Here's a crucial detail. The algorithm doesn't simply add up weighted factors to get a decision. Instead, it uses the weighted factors to calculate a probability between 0 and 1, of the decision resulting in continue. It uses a special function called sigmoid. As we can see, the sigmoid curve produces a smooth transition between 0, abort, and 1, continue, helping the algorithm adjust weights, so that cases where pilots continued, get probabilities above 0.5, and cases where pilots aborted, get probabilities below 0.5. The next step is to calculate the error in the algorithm's prediction, and this is where the probabilities come into play. Simply counting right versus wrong predictions like a traditional test score would be valuable, but it would not enable us to evolve the solution smoothly towards the correct combination of weights. Consider these scenarios. If the actual decision was continue, and the algorithm predicts a probability of 0.9, meaning a very confident continue, the error is small. If on the other hand it predicts 0.6, meaning a weak continue, the error is larger. But if it predicts 0.1, a confident abort, then the error from continue is already severe. So the total cost, or error, isn't just a count of mistakes. It's the average of these nuanced error penalties across all historical cases. Here we are entering the next stage, compute gradient. The algorithm computes mathematical derivatives that show exactly how adjusting each weight would change this total cost. If increasing a parameter weight by a small amount would reduce the average error across all cases, the adjustment in the next iteration will be upward. Alternatively, if decreasing it is what would help, we will see a slope points downward, indicating that a downward adjustment is needed. This gradient descent analysis is repeated for each of the weights and in each of the cases. Those of us familiar with calculus and gradients will now appreciate why a handful of cases may not be enough to create smooth curves, from which gradients can be measured, hence the need for many more data points than in the CBR method itself. Using the gradient information, the algorithm adjusts moves to update parameters. Here it will update all the weights simultaneously, each in the direction that its gradient suggested in order to reduce the overall error. The way the algorithm applies these adjustments is by heavily penalizing solutions in cases where the probability, which as we remember is the sigmoid function output, was below 0.5, but the actual pilot's decision was continue. It will also penalize in the same manner cases where the weights contributed to a value above 0.5, but the pilots chose to abort, namely 0. Here's a schematic overlay of interim solutions on the sigmoid graph, to further illustrate how the learning process works. The scattered black dots represent where historical cases might fall in an interim iteration, based on their weighted factor combinations. At the top and bottom are the actual pilot's decisions in the data, which are either 1.0, continue, or 0, abort. The algorithm's goal is to adjust the weights to increase the probabilities that predicted solutions reflect the decisions that were actually made. As a result, continue cases will move toward the top end of the graph, while abort cases will move toward the bottom. After each round of adjustments, the algorithm performs a convergence test, to see whether its predictions are improving. When the improvement between iterations becomes negligibly small, less than some threshold epsilon, the algorithm has converged. This iterative process could cycle hundreds or even thousands of times. In our example, we chose 2,400 cycles, or a change between iterations below a certain threshold, whichever occurs earlier. Once the iterative learning process converges, we now have weights that accurately reflect the historical decision patterns. And these weights will now be transferred to the CBR algorithm. It should be noted that the above process, using what is known as gradient descent, is almost identical to the one used for training neural networks and language models. The last block in the flowchart, model validation, is crucial if the algorithm is to be trusted and used in practice. Here we validate the model's accuracy and make sure it can correctly predict decisions on cases it hasn't seen before. Cross-validation techniques test this by training the algorithm on some historical cases, and then testing it on others. Finally, here's a screen capture video, showing the progression of the weights from the initial random condition to their final converged values after 2,400 cycles. As we can see, when conditions at the objective are challenging as in this example problem, the patient condition is a dominant factor in deciding whether to continue or abort.